Hello everyone, today we're going to be doing homework 2 for transport 2. We're going to start off by going over the context, the situation going on, and then we'll get into the questions. So essentially what we have here is a closed capillary tube. It is closed on both ends. And we have a divider right down in the middle. We have that the left side of the divider is 5 centimeters long and the right side of the divider of the tube is another 5 centimeters long. On each side of this capillary tube we have H2O on the left side and D2O on the right side. I wrote down that the volumes of both as volume H2O and volume D2O. That's just my way of identifying the volumes of both sides. Now, some givens that we have with this is we know that for sure it's a closed system. There's nothing that goes in, nothing that goes out, it stays like that. We know that H2O and D2O are both liquids. We also know that the molar diffusion flux, the maximum molar diffusion flux, once that divider is broken, is 2.78 moles over meters squared times seconds. We have the molecular weights of both D2O and H2O. The molecular weight of D2O is 20 grams per mole. The molecular weight of H2O is 18 grams per mole. We also have the densities of both of them. We have that the density of D2O is 1,110 kilograms over meters squared, or meters cubed, and the density of water is 1,000 kilograms over meters cubed. Lastly, we have it that for the first two problems, we're going to assume that the time is 0.1 seconds, so it's immediately, almost immediately, after the divider is broken up. So for our first problem, we're going to be solving for the overall mass flux corresponding to the maximum molar diffusion flux. To start that off, we're going to have the equation that the overall mass flux is equal to the sum of the individual mass fluxes. So the mass flux of H2O and the mass flux of D2O. Well, we still don't have these two values, yet we can solve for them. We're going to write those out with these equations that the mass flux of H2O and D2O are equal to their molecular weights times their molar fluxes. But now we run into the issue that we don't have their molar fluxes, yet we actually can solve for that as well. We're going to have the equations that the molar fluxes, the individual molar fluxes, are equal to the molar diffusive flux of the same component added to the mole fraction of that component times the overall mass, or molar flux, I apologize. But we actually have a bunch of components here now that, go around. We don't really know all those, but we can actually cut those out because we have this value of the overall molar flux, which we do know that is the sum of the individual molar fluxes. And because this is a closed system, this value must equal 0. So because this equals 0, we can replace these with 0, and since that's multiplied by that mole fraction, we can actually cut this whole part out. That those are 0. So by erasing that, we're going to see that this gets a lot simpler. Now we can see that the molar flux of H2O and the molar flux of D2O is equal to their corresponding molar diffusive fluxes, which is great because we actually have that value. But there's one more thing we need to note. The molar diffusive fluxes also add up to 0, as they are also part of the closed system. And because of that, we can deduce that they are both equal but opposite. Now we have the value of this actually right here, 2.78 moles over meters squared times second. But we need to know that they are going to be opposite. One's going to be positive and one's going to be negative. We're going to go under the assumption that to the right here, the H2O is going in the positive and the D2O is going in the negative end. So with that, we can take this number, 2.78 moles over meter squared times second, and replace it with these, but we'll make the molar flux of D2O negative and the molar flux of H2O positive. So we can rewrite this as equal to, and we also have the molecular weights here, the molecular weight of H2O being 18 grams per mole and the molecular weight of D2O being 20 grams per mole. We can rewrite this as 18 grams per mole times the 2.78 moles over meters squared times seconds but we also have to convert it to kilograms, so we'll have that in it. And the same applies for the D2O, except it is 20 grams per mole times the negative 2.78 moles over meters squared times seconds, and then convert it to kilograms. Which we can get for both of these factors, we get that the H2O is 0.0500, and that the D2O is 0.0556, negative, I'm sorry, it's negative 0.0556. Now that we have both H2O and D2O, we can actually solve this equation up here. We have both values. So we can get that as 0.0500 minus, it's supposed to be plus, but because of that negative, we're going to write it as a minus 0.0556, which leaves us with 0.0056, or we can write that as 5.6 times 10 to the negative 3. And that is in grams over meters squared times seconds. And that is the answer to find the overall mass flux. I apologize, I made a mistake. This is actually supposed to be negative. These values right here, when you subtract them, that ends up being negative. So for our second problem, we are trying to find the order of magnitude estimate for the maximum driving force for diffusion at t equals 0.1 seconds. I already wrote this all out, so I'm just going to go through and explain it as I go. Two things that we need to know are we're going to have two components. Component 1 will be the H2O side, and component 2 will be D2O. Now, starting this off, we have the equation for the driving force. And we have it all written up here, which right here we can see that the molar diffusive flux and the molar fraction actually cancel out up here and equal 0. And since the numerator is 0, this whole side becomes 0. So we only have to worry about this right side. Right over here we have the molar diffusive flux of component 1 is times the mole fraction of component 2 minus the molar diffusive flux of component 2 times the mole fraction of component 1, all over the total concentration, the total molar concentration, times the Stefan-Maxwell diffusivity of components 1 and 2. Now, this is a lot to take down. We're going to have to break this apart a bit. So let's start off by solving for the total molar concentration. We can have it right here with this equation that the total molar concentration equals the sum of all the individual concentrations. I actually was able to solve for that here because we have the densities and the molecular weights of both D2O and H2O. So with that, we are able to solve that the concentration for H2O component 1 is 55,555 moles per meters cubed, and the concentration of component 2, the D2O, is 55,500 moles per meters cubed. And we can see over here, the thing is, that is the concentration for the individual squares that they have. Assuming squares, they're not really squares, but the individual halves that they have. So because when we break it apart, the volume doubles, we have to put it all over twice the volume. We know that the volumes are the same, they are equal, And because of that, we can just assume that it's over 2 of volume on the H2O side or 2 of volume on the D2O side. It doesn't matter because they are equal to each other. Now with that, we have right here 55,555 over 2 meters cubed plus 55,500 over 2 meters cubed, and we get that the total molar concentration is 55,527.5 moles over meters cubed. So now we have the total concentration, which is great. That's one part of what we need to solve for. Next, we also need to find the Stefan-Maxwell diffusivity, which we know that since it is an ideal situation, we can actually say that the magnitude of that is 10 to the negative 9th meters squared over seconds. So now that we have that, we still need to solve for the top two, but we can actually cut that down a bit. So we know that the molar diffusive fluxes of component 1 and 2 add up to be 0. Because of that, we know that the molar diffusive flux of 1 is equal to the negative molar diffusive flux of 2, which we're going to use that and substitute it in to make this equation a little bit easier to go through. Another thing we should be aware of is that the sum of all of the mole fractions is equal to 1. Therefore, we're going to actually substitute the mole fraction of component 2 as 1 minus the mole fraction of component 1. And we have that written up here. We use those substitutes up here. That allows us to actually cut it down once you spread it out. And we have here that the molar diffusive flux of component 2 times the mole fraction of component 1 minus molar diffusive flux of component 2 times mole fraction of 1. That goes out, becomes 0. So all we have left is the molar diffusive flux of component 2 is a negative over the total concentration times the Stefan-Maxwell diffusivity. We already got all those values there, so actually the values is negative 2.78 moles over meters squared times seconds over the 55,527.5 moles over meters cubed times the 10 to the negative 9th meters squared per second, which we get that to be as negative 5.0065 times 10 to the 4th. And from that, we can actually find the magnitude, the order of magnitude for the driving force as 10 to the 4th. So for our final part of this homework, we are actually going to be graphing the situation that is going on with this capillary tube. Essentially, we're going to be graphing it at 3 different stages. The initial stage, where t equals 0.1 seconds, the intermediate stage, where t equals 60 seconds, and the final stage, where t is equal to the infinite end. There's no end, but infinite seconds. I have it written here as a key that anytime where we need to differentiate H2O and D2O, H2O will be the color blue and D2O will be the color red. Otherwise, it'll just be in pencil. So, starting off, a neat thing to note is that the x-axis of all of these graphs is going to be the different positions of the capillary tube. The capillary tube has a divider at 5 centimeters in the initial state, but that divider gets removed. And so from 0 to 5 is where the H2O starts, and from 5 to 10 is where the D2O starts. But that's where they begin to mix. So first we're going to be comparing that to the mass concentration. At the initial state where t equals 0.1 seconds, all of the H2O is on the left side. There really wasn't enough time for both of them to react. This is essentially right after the divider had been taken out. And so the the mass concentration of the water is 1,000 kilograms per meters cubed all across this left side. But at the divider, it drops down to 0 because there is no H2O on the right side. The opposite is for D2O. The D2O is at 0 on the left side from 0 to 5 centimeters, but it rises up to 1,110 kilograms per meter cubed once it hits the right side of the divider at 5 to 10 centimeters. We note that at the intermediate, where t equals 60 seconds, we can see that these are actually beginning to mix together, and we see more D2O on the left side and H2O on the right side, although the densities are still not at their 100% max where we have it here. They're beginning to mix around in there. and the slope is dropping, you can imagine this is just a very steep slope. As time passes, that slope is beginning to become less steep until we hit the final stage, where t is infinity, where the slope becomes 0, and we just have that the density of D2O and the density of H2O is the same across the entire capillary tube. For molar concentration of H2O and D2O, it's a similar situation. We have the molar concentration of H2O as 55.5 moles per liter, and the same is for D2O. It's a little bit less, but it's such a minute difference in this situation. And so we have that in the initial state where t equals 0.1, the H2O molar concentration is at that 55, but it drops down and it's 0 because it has not had enough time to mix. It has not moved over to the other side. Same goes for the D2O. It is a 0 from 0 to 5 centimeters before the divider, but at its side of the divider, it is at also 55 as well. Again, once time passes, once it hits the intermediate of t equals 60 seconds, you can see that this super steep slope, we can just imagine this as a steep slope, ends up kind of decreasing a little bit, and you can see that it's flattening out. You can see that there's more molar concentration of D2O on the left side of that, where that divider originally was, and more H2O on the right side. They're beginning to mix until we hit the point where it is equal across the entire board for H2O and D2O. It's kind of hard to see, but there is a blue line there and a red line as well. For the molar diffusive flux, we know that the maximum molar diffusive flux was 2.78, but we know that for H2O and D2O, they are equal but opposite. So you can see that the H2O's maximum molar diffusive flux hits the 2.78 at the top here, while the D2O's is negative 2.78. And you can see again that that slope is very steep, but it's 0 everywhere else. Why is that? And that's because this is where the divider was at t equals 0.1 seconds. It hasn't had enough time to move across to the other end. This is the initial state. You can see that once we get to the intermediate, 60 seconds, the slopes begin again becoming less steep across the board, and it spreads out further to the ends of the capillary tube. Now, another thing to note is that these two values are not equal to these two. They are a little bit less because at this time, that is where the maximum molar diffusive flux is. This is not where the max is. And again, these slopes will flatten out all the way until we hit t equals infinity, where we hit the equilibrium, and there is no more molar diffusive flux. Everything is evenly spread across, nothing needs to move around. For the mass flux, it's a similar situation. We deduced from question 1 that the mass flux, the overall mass flux, is negative 5.5 times 10 to the negative third. I just wrote the same thing on the top just to have an opposite end for it. And right here you can see it's again very steep at the beginning because there just wasn't enough time for the mass flux to spread across the entire capillary tube. It was just immediately, the divider was only just immediately removed. And you can see once we hit t equals 60 seconds, that slope actually does flatten out a little bit, but also the overall mass flux lowers. It's not as high as it was in the initial state of the divider being removed. And that goes all the way out until we hit t equals infinity, where it is at equilibrium. There is no more mass flux, nothing is being moved, everything is steady and spread across evenly.